Okay. Next participant. Okay, so we are live again there at YouTube, and in a few minutes we can start with our first speaker in this last section of ISP 2020. This section is really a nice one because we are bringing as speakers some of our alumni, some of our students here of UFCG postgraduate program, and also a special guest who is Clarissa Siqueira. So I thank you all, the former students, for being here, and it's going to be really nice to hear your presentations. And so our first speaker in this afternoon is going to be Simony Costa. And I would like to call Professor Carlos Bessa to introduce our next speaker. So Professor Carlos, please, the word is yours.
Okay, thank you. Thanks a lot, João. Next speaker is Simony Costa. She is PhD in astronomy from the Observatório Nacional, Rio de Janeiro, Brazil, and Universidade de Studi di Napoli, Italy. And currently she is postdoc at Observatório Nacional. Her research topics are inflationary observational tests, constraints over theories of gravity. And she was master student at UFCG, supervised by Professor Rodrigo Holanda. So, Simony, you have about 25 minutes for your talk, okay? Thanks.
Okay, thank you. Thank you all. Let me share my screen. Someone has to enable, oh, okay. So can you see my screen?
Yes,
yes,
we are seeing.
Yes, we can.
Okay. Hello, everyone. I would like to thank the organizing committee for inviting me to be here today. It's a pleasure being ex-student from USCG and come back here today to talk about my work. And today I'll present to you some constraints, some observational constraints on brain inflation. This presentation is based on two works that I developed in collaboration with my supervisor, Jailson Alcanis, Mico Benetti, Francisco Brito, Raíssa Neves, and Raimundo Silva. So the outline of my presentation is the following. We can start asking, why do we need inflationary phase in the universe? How can we relate inflation with the modified theories of gravity? I'll present briefly the slow roll analysis, a kind of analysis that we need to know if some models are capable to realize inflation. And I'll present two models that we have studied. The first one is more kind of testing the robustness of the Starobinsky model. And then I'll present a brain inflation scenario with an arc tangent potential and some final remarks. So the question, why do we need inflation in order to build a viable cosmological model, comes from the fact that we have some open problems in the Big Bang cosmology, such as the horizon problem. And also because with inflation, we can provide a natural explanation for the fluctuations of the cosmic microwave background radiation, and also for the growth of the large scale structures that we observe in the universe. So the simplest realizations that we have to perform inflation is to consider a scalar field that dominates in the primordial universe and whose potential energy dominates over the kinetic term in such a way that we can have this equation of state parameter equals to -1. That is the same that we have today for the universe accelerated. But in this case, we cannot use dark energy, for example, because inflation could never end. And so the alternative is to use the scalar fields with some potential that dominates over the kinetic term. And so we can drive inflation with this scalar field in the very beginning. But the very first model that addressed the inflation scenario was the Starobinsky model that considers quadratic corrections of the ridge scalar and the Einstein-Hilbert action. So instead of have just the ridge scalar here on the action, we replace for a f of r function that includes this quadratic term of ridge scalar. But if we make a conformal transformation of the metric, we can rewrite this action in the Einstein frame, and we call this Einstein frame because we can recover the Einstein field equations because we have just the ridge scalar and we have this effective potential that is related with the f of r function in this way here. So it's equivalent if we treat inflation consider a function f of r in this way, or if we consider a potential of this type here that is an exponential. So both of them are the Starobinsky models, and they are sufficiently good to describe this inflationary period that we had in the beginning of the universe. The slow roll phase is the slow roll analysis, sorry, is what we need to guarantee that that period of accelerated expansion in the primordial universe was exponentially, and that means that the Hubble parameter age must be almost constant, so its variation is close to 0, and we can quantify these also through this relation here. So the variation of the Hubble parameter in a time 1 over age must be smaller than 1. And this is what happened when the potential energy dominates over the kinetic field. Over the kinetic term, the potential is slowly rolling down its potential until achieve the minimum. And so the inflation ends, and we have the posterior cosmological eras, that is the radiation dominated and matter dominated, and now the accelerated phase again. And we can describe models that can perform or not inflation through what we call slow roll parameters. So the first one is that I told you before. That's the variation of the Hubble parameter that must be close to 0. We quantify this through this parameter epsilon. And this other parameter eta that guarantees that the variation of the potential is slowly rolling down the potential, the scalar field. Only the potential energy is dominated. So we guarantee this if this parameter eta is also much smaller than 1. So, and plus we can, instead of write the slow roll parameters with the Hubble parameter or the scalar field, we can translate this to the potential and to the derivatives of the potential with relation to the field. So we can characterize a model and know if it's perform inflation since these both conditions are valid. And we can also quantify how much inflation do we need in order to solve the horizon problem, for example, or in order to produce the observed pattern in the cosmic microwave background through the number of E-folds that quantifies how much the universe expanded exponentially through the discount here that is just the integration of the logarithm of the scale factor, and that we can also write in terms of these slow roll parameters. So once you have the potential, we can write the derivative and we can write the epsilon, and so we can calculate how much the universe expanded exponentially, and so make the predictions for our models. Okay, so one more thing is that this scalar field fluctuates. So these oscillations, these quantum fluctuations of this scalar field during the inflation, which means while it's slowly rolling down its potential, is the origin of the cosmological perturbations, and is the origin of the fluctuations of temperature in the CMB. And also we have tensor perturbation, not only scalar perturbations, that perturbations in the matter that we can relate with temperature, but also in the tensor perturbations that we can quantify, for example, through a parameter that we call tensor to scalar ratio, that quantify the amount of gravitational or primordial gravitational waves that we have. So generally, what we do is to parameterize these cosmological perturbations through a power spectrum that can be written in this form here, a power law, and with this scalar spectral index be written in terms of that slow roll parameters that I told you before, and also the tensor to scalar ratio. So what this plot tells us, here we can see contour regions. The gray one is considering just temperature data from Planck. The red one is considering temperature data plus B-mode polarization, and the blue contours are the regions obtained considering temperature, B-mode polarization, and also baryonic acoustic oscillations. So this means that the data predicts or prefer values of NS and R that are inside these regions. So the most in turn is the, is 68% level, and in this one is 95% level. So if you have a model, and for example, here we have different types of potential, polynomial potential with different exponents, we can calculate the slow roll parameters, epsilon and eta, and with epsilon and eta, we can calculate NS and R, and we can make predictions. We can make predictions for our model. And if your model predicts something that is inside this region, it means that it could be a good model to describe inflation that predicts an invariant scale power spectrum, and that could produce the fluctuations of temperature in the CMB as we observe. But for example, here, this potential, that is a cubic potential, predicts a value of NS that is okay, but it predicts a lot of primordial gravitational waves. And we didn't observe primordial gravitational waves. We just have an upper limit that in this case is smaller than 0.1. So we can discard this type of potential to describe inflation. We remain, for example, with this one here, that is the R2 inflation or the Starobinsky inflation, that also that potential with the exponential. And that's the best model we have today to describe inflation, because the predictions are well inside the confidence region. So this is what we gonna do here. And this is what a lot of people have been doing during time. And we have a lot of models to describe inflations, a lot of potentials. And when the first release of Planck data was available, the Jérôme Martin and collaborators investigated 1903 or 1906 models of inflation, of potential inflation. And they made a Bayesian analysis, and they could discard with strong evidence 34% of these models, with moderate evidence 17% of these models, 21% with weak evidence these models. 26% of all those models relies on the evidence that we call inconclusive. So they are as good as the Starobinsky model, that was the reference model, but they are not better than the Starobinsky model. So we have that the Starobinsky model that I showed you here, that is well inside this region, is the best model through this rich amount of models that we have for inflation. And here I'm just showing you models with one field, single field inflation. We can have two field inflation and more. And by other hand, we also have this potential, this Starobinsky potential arising from different inflationary scenarios. We can recover the Starobinsky model from a Higgs model with a non-minimal coupling to gravity, with simple locally conforming invariant theory, with and spontaneous symmetry breaking, superconformal theories, supergravity in the F of R theories or higher order, and also from string models with using the Nader symmetry approach. So by one hand, we have a lot of scenarios that are capable to recover the Starobinsky model in a more fundamental theory of physics. And by the observational side, we have that the Starobinsky model is the best model to describe inflation. So we first aim here, the first part of presentation, we decided to investigate how robust is this model. How can we deviate from the Starobinsky model and still describe well the data? So we investigate this considering a scenario of Brane inflation. Okay, in general, in the Brane inflation, what happens is that the universe we live are contained in this brane of 3+1 dimension that is immersed in a book of higher dimension, in this case 5 dimensions. So we have one extra dimension. And the fact that the only gravity can propagate in this extra dimension made possible that induced potential here in 4 dimension can drive inflation. So in this case here, that more than one, Francisco Brito, Jailson Alcanis, and Michael Bennett have studied before a case where the Brane inflation induced this kind of potential in 4 dimensions, and this can drive inflation. So here L is the is the position of the Brane along the extra dimension. C1 and lambda are also parameters of the extra dimension. And if we made some considerations, we can recover this potential here. That is an extension of the Starobinsky model. And we are one more of the people that recover the Starobinsky model from a more general scenario or a more fundamental theory of physics. And in this case, what happened? If you remember, the Starobinsky potential has, instead of this term, has an exponential. So if you remember, it's this exponential that in this case we can recover a beta exponential function that has this property here, and so we can write the generalized Starobinsky potential in this way here. And this parameter beta is the parameter that quantifies how much we can deviate from Starobinsky and continues to describe well the data. Okay, so as I showed you before, we have kind of general recipe to study models of inflation. So the first step is you have a potential, you can calculate the slow roll parameters, epsilon and eta, and see if those conditions of epsilon and eta are much smaller than 1, then this potential can perform inflation. The next step is to obtain the predictions for the parameters NS and R and investigate if they are in agreement with the region that is allowed by the data. And last, we can calculate the primordial power spectrum and also the angular power spectrum of temperature fluctuations of CMB. CMB is the cosmic microwave background. And so we can confront with the model with the data and constrain the cosmological parameters and obtain a more robust analysis for the model under consideration. So for the extended Starobinsky potential, we can write the slow roll parameters epsilon and eta in this way, where we have this term chi that depends on beta and on phi, just for rewrite here. And with epsilon and eta, we can write the parameters ns and r. With this theoretical ns and r, we can see what are the predictions in the NSR plane. So that's the same of before. And here the blue contour shows the 68% and 95% of the confidence regions using just the temperature data from Planck. And what we see is that for different values of beta, we have different predictions for the pair NSR that are all inside the region that are allowed by the data. And this is good. But for the same reason, this is not so good because if all the predictions are inside the region that is allowed by the data, we cannot discriminate what is the best value for beta and what's the best value for this parameter describe the data. But we can put limits on the range of beta. So for example, for values of beta bigger than 0.2, we expect to have negative values of the parameter R, which is unphysical. So we can put this upper limit to beta, that is 0.2. And we go to the other side and consider values smaller than -4. What we get is predictions outside this region. So it's not interesting. So we have these two limits now, this lower limit of -4 because smallest values will predict something outside the region, and the upper limit of 0.2. So the next step is to, so in general, most of people do this. So goes to the NSR plan and see that the model predicts good values for NSNR that are allowed by the data, and so this model could represent the inflationary phase. But we can go further and also investigate how the other cosmological parameters behaves in this kind of models. To do that, we can use the code for anisotropies in the microwave background, the CAMP code that calculates the primordial power spectrum and the temperature power spectrum of the fluctuations of temperature of CMB. And we can use the CosmoMC code, that is a Markov chain Monte Carlo code to explore the parameter space, solving the Boltzmann equations. But one thing is that CAMB used that parameterization for the primordial power spectrum, that is calculated in terms of this NS and this amplitude, scalar amplitude here. But when we are considering models with potential, we can use a different code, that is the mode code, that solve the dynamical equations, the Friedman equation for the Hubble parameter and the Klein-Gordon equation for the field. And with these solutions, they can solve the Mukhanov-Saslak equations. And with these solutions, we can construct the primordial power spectrum in this way. And once we have the primordial power spectrum, we can also calculate the temperature power spectrum, and we can then explore all the parameter space and constrain all the cosmological parameters. So we have to modify mode code and CosmoMC to include our potential to solve these equations and to obtain this primordial power spectrum here. And what we get from this is these predictions, these theoretical predictions for the temperature angular power spectrum. So the Starobinsky model is this dashed line, dashed black line that, believe me, is here, down here somewhere. Here we can see better. And these points are the observational data. So the Starobinsky model is a very good model. We already seen that. And what is the effect of including this extra parameter beta is that we have basically this slight one slightly change here in the first peak of the temperature power spectrum that can see better, that we can see better here in this residual plot. So, but again, we are not able to say what is the best value for beta. To do that, we have to explore all the cosmological parameter space, and we do that running Markov chain Monte Carlo with CosmoMC. And when we do that, we must use some observational data. And what kind of data is the best for we confront with these models is the CMB data, CMB temperature data, and the baryon-Lacusse oscillations, because the inflationary period, remember, imprints the fluctuations of the quantum, imprints the quantum fluctuations of the scalar field in the fluctuations of temperature in the CMB, and these fluctuations of temperature are related with density fluctuations that grows gravitationally to form the large-scale structures that we observe in the universe. So we can use this data set, CMB plus BAO, and we can constrain all the cosmological parameters. So here are the results for the Starobinsky model and for this beta Starobinsky model. All the cosmological parameters are in good agreement with the Starobinsky model and in 1 sigma, and we found no evidence for a value of beta different from 0, because here 0 is included in 1 standard deviation. But the difference is that we have a more tighter constraint for the tensor to scalar ratio. Instead, here in the Starobinsky model, we can just predict one value, and here we can derive this constraint. But we can compare these models and see if it's valid to consider a model more complex with one more parameter that describe the data as well as the Starobinsky model. We can do that using the Bayesian information criterion that consider the value of the parameters that maximize the likelihood, but also considers the extra parameters and the number of data points that we use. And calculating this quantity here, we find a positive preference for the Starobinsky model over the beta Starobinsky model, which means that this model is good, describes well the data, but it adds more complexity that is penalized here with this quantity. So it's good, yes, it's good, but we cannot add another. We do not need to add other parameter if we describe the data as good as well with a minimal model. Here's just the confidence regions in the posterior distribution for the Starobinsky model in blue and beta Starobinsky model in green. And just what I have told you, that they are in very good agreement with the Starobinsky model, that is this dotted line here. Okay, here just the best fit values, and we see that this model is as good as the Starobinsky model, but the big value prefers the standard one. Okay, the second case, if I have time, we consider another scenario of brane inflation that now is a brane immersed in a book of 5 dimensions, but it's Minkowski space. And here in this case, we have an effective potential induced in 4 dimensions that is of this type here, an arctangent potential. So the procedure is the same. We can start calculating the slow roll parameters that has this form here, and so when we apply to this potential, we obtain this. With the slow roll parameters epsilon and eta, we can construct the NS and R, and we can make the theoretical predictions for the NSR plane. And here's what happens for these forms of NS and R. We consider different values of beta, since 0.1 to 10 in this case. And what we can see from here is that values of beta small than 5 are outside the region that is allowed by the data. So we can constrain the range of beta that allow us to use this model to describe inflation from 5 to 10, kind of this. And now we proceed to the Cosmology analysis. This behavior here that we can exclude these values of 5 also can be seen here in the theoretical predictions for the temperature power spectrum. So if we look here, small values of beta predicts a much smaller amplitude for the temperature power spectrum, and so we can discard this for describe the data that are these points here. But for values between 5 and 8, here we have something close to the data that we can adjust, constrain all the cosmological parameters. So that's what we do with the Cosmology analysis, and we obtain these constraints here. So the baryon density, the cold dark matter density, the theta parameter, that is the ratio between the last surface at the coupling, and the tau, that is the cosmic opacity, no, optical depth, and the beta parameter. And we can also put constraints on the Hubble parameter today, density of matter, density of dark energy, and also in the NS and R values. So all these values are in good agreement with the lambda CDM model, and maybe it's the first time that we put constraints on this parameter beta for this kind of potential using the observational data. Here are also the 2D probability distribution and the posterior distribution. We can see that the parameters are well constrained. It's the same of the table, but just in plots. And here are the best fit values. So if you remember, the theoretical predictions here for values of between 5 and 8 has a different amplitude.
Sorry, more 2 minutes, okay?
Okay, I'm finishing. So these values between 5 and 8 are close to the data, but when we vary the other cosmological parameters, we can obtain this best fit value for beta, that is 6.97, and we can adjust this model to the data as well as the lambda CDM model. And the final remarks is this: we investigate the robustness of the Starobinski model, inserting it in a general framework of Brane inflation, and our statistical analysis has confirmed its remarkable success to describe current observational data. The analysis we performed for the arctangent model corroborates to its observational viability and establish the general theoretical predictions for the model. And we aim to include the effects of reheating in both models in a future work. And thank you all, and questions are welcome.
Thank you, Simony. So we have time. I think we have time for one question. Quick question.
I have a question.
Yeah, we had some problems.
Yeah.
Let's see YouTube.
Hello. Can you hear me now?
Téssio, your microphone is really noisy.
Yeah, I can't see any questions here. So I don't know if you see anything wrong. If someone raise his hands, because I can see here, but
Well, I have one. problem, Téssio.
Yeah, Téssio had a problem with your microphone. So I think we don't have questions. So, okay, thank you, Simony.
Thank you.
Thank you a lot for a very nice talk.
Thank you.
So next speaker is Téssio Melo. I hope your microphone is...
Maybe you can use the microphone of your computer, Téssio.
Let's try.
But one has a problem. No. Téssio?
And now, can you hear me?
Yes, now it's much better.
Okay, let me try to get back to the phones. You're hearing me now?
Yes.
Yes.
Oh, nice, okay.
Okay, so next speaker is Téssio Melo. He is PhD in Physics at Universidade Federal da Paraíba, in João Pessoa, Brazil, and currently he is postdoc at International Institute of Physics in Natal, Brazil. His research interests are particle physics beyond the standard model, and dark matter and nanoparticles. And he was a master student at Universidade Federal de Campina Grande, supervised by Professor Diego Cogolo. So thanks a lot, Téssio, to share with us your work, and you have about 15 minutes, okay?
Okay, thanks a lot for the introduction. Let me try to share my screen. Can you see my screen?
Yes, we can.
Okay. So let me put in full screen. Okay, so first I'd like to thank the organizers for this nice invitation to give me the opportunity to give this talk. And to me, it's really a pleasure to be here, to be back to Campina, at least in a virtual way. Hopefully, in the next editions of this symposium, we can meet in person. It will be very nice. So, yeah, my name is Téssio Melo. I'm from the International Institute of Physics. And today I'm going to talk about a new experimental result from a dark matter experiment, which is the Zeno-Monton experiment. And I will try to describe a proposal by us to explain this experimental result. So this is the outline of the talk. First, I will try to describe the working of the Zeno experiment and what was the signal that they observed there. Then I'll move on to introduce our model to account for this experiment, and then describe our results. So this presentation is based on these two papers. The first one came out this year after the announcement of the Zeno result, done in collaboration with Manfred Lindner, Jan Mambrini, and Farinello Queiroz. And this one, a bit older paper, in which we first introduced this model, which we now use to try to explain this data. done in collaboration also with Manfred Lima and Fernando Queiroz, and also with Professor Diego Cogolo from the physics department of the UFCG. So the Zeno experiment, as most of you might know, around 27% of the matter energy budget of our universe is in the form of a matter, which we don't know what is, but we know that it exists because of its gravitational effects. So there is a huge international effort to search, to detect these dark matter particles. And the Zeno one-ton experiment is one of these experiments that try to directly detect this dark matter. So what's this experiment? So basically it's a tank which is full of xenon. There is about 1 ton of liquid xenon. That's why the experiment is called xenon 1 ton. And there is also gas in the top of the tank. So what this experiment does, it basically measures these two signals S1 and S2. I will try to explain what are those. So imagine that a particle gets inside the tank. This particle can interact with the xenon atoms, and as a result of this interaction, two things can happen. First, there is emission of photons via scintillation. The xenon atoms excite, and in the de-excitation, photons are released, and these photons are collected in the photomultipliers at the top and the bottom of the tank. So this is the signal S1. And also this interaction can result in ionization. So there will be free electrons, and there is a electric field applied vertically in the tank. So these electrons will be drift towards the top of the tank so that they reach the gas phase. And in the gas, the electrons emit photons by electroluminescence. So this is the S2 signal. So basically what the experiment measure is these two signals, and they count the number of events over time. Okay. One important piece of information is that the experiment is able to discriminate between nuclear and electronic recoils. So the neutral particle that gets into the tank can interact both with the nucleus of the xenon atom, but also with the electrons. And it is possible to discriminate between them in this, looking at this plane in which you have these two signals. There is a characteristic band for nuclear recoils and another band for electron recoils. So this is important because in the standard dark matter scenario, it is expected that these dark matter particles produce nuclear recoils. But in June of this year, the Xenon collaboration announced this result in which they found an excess on the electronic recoils. So in this region between 1 and 7 kV, they expected to see about 230 events, and they actually see 285 events. And this means an excess of around 3.3 sigma of statistical significance. So as you can see here in this plot, around here 2 to 3 kV, at these energies, the data start to depart from the expected number of events. This red line is the expected number predicted by the standard model. So this is somewhat surprising because, like I said, this is not one would expect from a dark matter particle. Okay, and what can be the cause of this signal? Well, there are some possibilities. It can be just a background that was not taken into account properly by the collaboration. It can also be a statistical fluctuation. The statistical significance is not that high, so we can discard this possibility, okay? But of course, we hope that this is a genuine new physics signal. And we try to explain this signal not in terms of a dark matter particle, because it is, again, it is not one would expect from a standard wave. But we tried to look at other directions, and we thought that, okay, neutral particles can get inside the detector, including neutrinos. And it may be possible that neutrinos are producing this excess. So one thing which is very interesting to notice is that the excess didn't happen at some place, at some random place in the energetic spectrum. It is rather localized in the low energy tail of the spectrum, here very close to the detector threshold. And this is interesting because there are some new physics scenarios in which scattering cross-sections get enhanced at lower energies. And these enhancements can be blind to our detectors just because the detector has not low enough threshold, okay? So this is precisely what happens with neutrinos interacting with electrons if there is a new fundamental interaction connecting them. So as you can see here in this plot, we have here this scattering cross-section for this process. At lower energies, this cross-section gets enhanced, goes like the inverse of the energy. So at lower energies, it gets enhanced a lot. And it's just what we need to reproduce this data at lower energies. So that's our hypothesis here, that neutrinos can interact with electrons via a new fundamental force, which is mediated by this particle here that we call Z prime. And where these neutrinos come from? Well, they come from the sun. The sun emits a lot of neutrinos all the time. And these neutrinos can reach the detector and hit the electrons inside the Zeno experiment. Okay. So yeah, I'm not. I'll just skip this. It's just to say that we need gauge symmetry to give rise to this new gauge boson, this Z prime. And in our model, this symmetry is well motivated by completely unrelated regions. And just to say, it's to solve the so-called flavor problem here. But I will not get into the details of this. It's just to say that we already needed this new symmetry for other regions. And as a bonus, we get exactly what we need to explain the xenon result. So I think this is a very nice feature in our proposal. So the interactions of the Z prime will be controlled by these two parameters, the kinetic mixing and the gauge coupling constant. And once we fix the charges, the symmetry here we are focusing on is the B minus L symmetry, which means that the charges of the particles under this new symmetry will be its baryon number minus its lepton number. Okay, so this sets the strength in which the Z prime interacts with the fermions of the standard model. So, okay, with everything fixed, we can start to do the calculations. So here I'm showing the scattering cross-section for this process, the neutrinos interacting elastically with the electrons via the Z prime. And we can see here that the cross-section has this behavior. It goes as the inverse squared of the electron recoil energies. And this will display this enhancement here if the value of the Z prime mass is very small. And small here means small compared to the electron mass. So for instance, for a Z prime mass of order 10 keV, which is shown in this blue curve here, it's very explicit, the enhancement. But if we increase this mass to around 500 kVs, this green curve here, we don't have an enhancement at all. So this mass are determined by the strength of the interactions we need to reproduce the data, and it requires that this mass is very small. So yeah, that's a bit technical. It's just to how we can compare our predictions with the experimental data. We have to take into account all the neutrinos that come from the sun. There are several different sources. We have to take this into account so that we can compute this event rate. Okay. So here is our main result. In this plot, we have the experimental data, which are these black dots. And the curves here represent the predictions of our model. Yes, this red dashed line here is not from our model, is the prediction of the standard model. Okay, so as you can see here, for a small mass of Z prime of 10 keV, we have a peak, a very pronounced peak, which follows almost perfectly the experimental data, and then falls off to reproduce this other point here. So it's a very nice fit. If we increase this mass to 50 keV, the height of the peak gets smaller, but anyway, it's a better fit as compared to the standard model. So in fact, we have a range of masses that are allowed for the Z prime to provide a good fit to the data, which is shown more clearly in this plot. Here, this green region represents the range of values allowed for the masses of the Z prime and for the strength of the interaction, in which is possible to provide a good fit to the data. Okay. So to summarize, the take-home message is that there is a new experimental result. There is an excess which could point to the existence of new physics from the Xenon experiment. This is not what would naively expect from a dark matter particle. So the origin of the signal might be related to other kinds of new physics. And here we proposed a model which relies on the existence of a new fundamental interaction which allows the neutrinos interact more strongly with the electrons, and this can be what Zimmermann is seeing. Okay, so we characterize this new interaction, saying what's the range allowed for its strength and the mass of the mediator, so that we can reproduce the experimental data. So yeah, that's all I had to say. And thank you for your attention.
Okay, thanks a lot, Téssio. I think we don't have questions here in my panel and not even in the YouTube. So we finish here.
Okay, Carlos?
Oh, see, yes.
I guess I have a quick question, maybe.
Okay.
So thank you so much, Téssio, for this nice talk and really interesting subject. I'd like to ask, well, if you are working on other possible, let's say, sources where you could see this kind of fundamental force also appearing instead of just this case of this excess found in this specific experiment, because if it is really a fundamental force, it should appear, I guess, in other kind of scenarios too, or in other kind of experiments.
Yes, so it's a great question. Thank you, Ron. Yes, you're right. This force can manifest itself in other kinds of experiment. And in fact, we are working on how this light mediator can show up in other experiments. It can, for instance, be produced in the case of the Higgs boson at the LHC. We are working on this right now. And there are many more experiments that can prove the existence of this interaction. There are low energy experiments which have dedicated searches for this kind of particles. And yeah, we are working on that with this other signatures and other experiments.
Nice, thank you so much again. It was a pleasure.
Okay, thank you, Téssio. I think we don't have time to any other questions, so thanks a lot for this very nice talk. Okay, and now I would like to introduce the next speaker. Is Klécio Lima. Klécio is studying his PhD at Universidade Federal da Paraíba in João Pessoa, Brazil, and his research interests are field theory and quantum vacuum fluctuations. And he was master student at UFCG, supervised by Professor Eduardo Passos. Okay, Klécio, you have 15 minutes, okay?
Okay. Can you hear me?
Yes, very. And we can see you.
Okay.
Your slides.
Okay, thanks. So, first, thanks for the invitation to the event. And I will talk about quantum fluctuations effect in the quasi-periodically identified conical spacetime. This is based on the paper. It was made by me and my divisor, and it will be part of my PhD thesis. So this is the schedule of my presentation. I will start with a brief introduction about the theme. So quantum fluctuations arise quantum vacuum fluctuations effects arise when we perturb the quantum vacuum of a relativistic field. This perturbation can be made by implementation of boundary conditions or by external fields. These effects also take place when we have covered spacetime due to the non-trivial topology. Then we used we made an analog model to study the properties of the quasi-periodic boundary conditions applied in this situation, and we use the inspired in carbon nanotubes. Okay, the first step is to calculate the Whiteman function, and we have the line element described by the conical spacetime. Conical spacetime can be cosmic string or declination. And we have our boundary conditions, and that is quasi-periodic boundary condition. It obeys this equation, where beta is a parameter defining the interval between 0 and 1. So this equation 3 is the action of our theory in covered space-time, and when we apply the line element, we can we have the Klein-Gordon equation for minimally coupled scalar field. And when we solve this equation, this partial differential equation, we obtain this solution, and this solution must obey also the quasi-periodic boundary condition. Observe that this solution is in function of this J function, where it is a Bessel function of first kind. So, since we have the solution of, we can calculate the Whiteman function by using this expression. A lot of calculus, and we can find this closed expression of Whiteman function, where this f function is defined by McDonald function, and write in this form. And the sigma functions in argument are given by this expression, these expressions. Okay, so now we have the Whiteman function. We can calculate the vacuum expectation value of a phi squared, and we find it when we take the coincidence limit of a Whiteman function. But when we take the when we make this process, we have a divergent term in Whiteman function. Then we must subtract it by the Hadamard function, and we renormalized the phi squared term and obtain this equation, where this m function is given by this expression, and we have we must observe some points here. So this function, when we take beta equal to 0 and q equal to 1, this term is equal to 0. It is straightforward to see. It's not so difficult. But this term exists just when we have q greater than 2. Then if q is equal to 1, and the value of vacuum expectation value of the field squared is equal to 0, where as should it be. So However, the fluctuations of the quantum vacuum of the scalar field does not average to 0 for the renormalized expectation value for a massive case. This is due to the introduction of a boundary condition. So now I can the next step is to calculate the vacuum expectation value of the energy momentum tensor, and this we can find the energy momentum tensor is written in terms of Weizmann function and phi squared. Then calculating this, we find this expression, where this term is the all terms of our energy momentum tensor, but the terms of diagonal are the terms non-zero. The other terms are zero value. Then we plotted the vacuum energy density, where it's given by the energy tensor in 0, coordinates, and we plotted two forms in terms of mr, where when we take r to infinity, it goes to 0, and we plotted in terms of beta to observe the behavior of this function. Okay. So, and finally, we proved that the vacuum expectation value of the energy momentum tensor also satisfies the covariant conservation condition given by this expression and the trace identity for the massive charge scalar field. From that is this equation. Sorry. So, and the last physical observable is the induced coherent density, where it is formally given by this equation. So this induced density, we have just the phi coordinates because the action of the theory is invariant under the quasi-periodic boundary condition, according to the Nucleare's theorem. Just in phi coordinates, we have a non-zero azimuthal coherent density. Then we plotted also, we calculate the coherent density and obtain this form, this equation. So, and as well as before we had, now the Q, for Q equal to 1, this first term doesn't exist. Then it must Q for this term, Q must be greater than 2. So we plotted this function also. So in the same terms, or in terms of m times l, where when you take the limit to infinity for to l, it goes to 0 also. And in terms of beta, we have this behavior. Is really interesting because in 0 and beta equal a 0 and on it is 0, but also in beta equal 1/2, and it is expected. It is expected because at this value is was already studied in the literature, and our result is in according. So, but when we take the another values for beta, we have an induced coherent density. Okay. So to conclude, we concluded the modification on quantum vacuum fluctuations on charged scalar field caused by our boundary condition in conical caused by the boundary condition and the conical parameter settled average to physical observables analyzed to non-zero values. And by considering a charged scalar field modes propagate in a conical space-time subjected to a non-periodic condition, we have a generalized the results reported in the literature. So here I treated just the massive case, but in our paper we take all possible cases to analyze it, because we have a short time. So if you have a question, this is all I have. So if you have a question, you can ask now in English or Portuguese. Feel free to choose the language. So this is the bibliography I have used, and thanks for your attention.
Okay, thank you, Klécio. Thanks a lot. I can't see any question here. Let's see in the YouTube. Oh, no questions. So I have a quick question. You say what's the other cases you study? You said now in the end that
we study the massless case and the limits where when we don't have the boundary condition, or that is beta to 0, and in Minkowski spacetime when Q equal to 1.
Okay, so no dispute. Okay. Okay.
Okay. Thank you again.
Nice. Let's see, we still have time for one question.
Yes.
Let's see. People are shy, the participants. No question in YouTube. Okay, just Julia Aleixo is saying that you arrasou. Julia Aleixo is saying just that you arrasou. Okay, so thanks for this very nice talk and this very interesting topic. So next, let's introduce the next speaker. Next speaker is Ozório Holanda.
Yeah.
Right. He is PhD in physics at State University of Rio de Janeiro, and currently he is postdoc at Universidade Federal do ABC in Santo André, Brazil. His research topics of interest are Lorentz violation, supersymmetry, and normalization engaged fields. And he was master student at Universidade Federal de Campina Grande, supervised by Professor Eduardo Passos. Okay, Ozório, thanks a lot.
Yeah, thanks for the words, and I will share my screen.
Okay, you have 15 minutes, okay?
Okay.
Okay, I can see your screen.
Yeah, let me put in full screen that. Yeah, I would thank you for the words, and I would like to thank the Professor João for the invitation. And today I will talk about the renormalizability of N equal 1 super Young Mills theory in Landau gauge with a Stueckelberg-like field. My outline consists by an introduction, motivation. I will present the model, and you try to resume a little bit about algebraic renormalization procedure and conclusions and future works. So the objectives of these works is construct a BRST invariant superfield, and they try to do a massive excitation for n equal 1 super-Yang-Mills theory, and analyze the stability and the renormalizability of this model. So what's the main motivation to study massive Yang-Mills models in low energy? The first thing is because you are trying to understand the confinement of quark and gluons. It's an open problem in Yang-Mills theories. And you have observation using Monte Carlo computational simulations, or let's say QCD, that indicates have a massive behavior in low energy. And you can see that this graphic, I plot a graphic here from the Professor Coutier and Mendes using the simulations, that you can see this massive behavior. When P goes to 0, you have a saturated gluon propagator. And yeah, this Let's QCD is using numerical simulations. And the first idea is try to find a model or to build a model from first principles to explain analytically this massive behavior. So in quantum field theory, the first idea that we have when you try to put a mass in a model, you can, if you don't have a Higgs mechanism work in this range, you could think, you can put this in an easy way. The more easy way to implement that is put the mass by hand. You can use the non-abelian Procca model for that. This model is renormalizable, but you break the BRST symmetry. So you can think like that. I will try to fix this BRST symmetry. I will put my mass with some auxiliary fields and a gauge boson to try to fix the BRC symmetry, but you lose your renormalizability. So, by some works from the literature, and the Professor Sorella in Werge, the group there work a lot with that, and by minimizing a functional or gauge orbit that is represented mathematically like that, with this functional, you can get a very special field, because you know the derivative in this bound is equal 0, and you have a transversal field on that. And another interesting feature that you can write this field as a Stueckelberg-like field, like this auxiliary field. And if you have a Stueckelberg-like field, you have something that is BRC invariant. So if you have these features, you can use that to define an action. That's the action in the end. You have two properties of the Procca model and the Stueckelberg. You have one more strong model because you preserve this BRC symmetry, and you show the stability of the model and normalization, and you can work in physical things like confinement. And yeah, so very good model. And what I start to do in my PhD was that I think, what if you can extend that for supersymmetry, because supersymmetries are confining. N equal 1 supersymmetry, N equal 2, N equal 4 is a confining theory. If you can extend this for a supersymmetric background, we can work, and we can see what happens. And we did that, use the same idea of Stueckelberg, try to put some auxiliary fields to try to recover the BRC invariance of this field. And you can build that. You can use the equation 5 with the all gauge transformations inside the equation 4, and you can show in the end that is gauge invariant. So once you have this object that is BRC invariant, you can use that to build a model. And you start with this pure super Yang-Mills theory. It's just the super strength field, and you can put the mass by hand with this functional V8. This functional V8 is just because you don't have V8 like in AMI. in the Proc or Stueckelberg model, because in supersymmetry, the super gauge field is a scalar. There is no mass dimension in a Lagrangian, and in the general form, you can put a power series of that or a functional, just question of to write that in a general way. So in the second line, you have the Landau gauge. You fix the Landau gauge using these Lagrangian multipliers. You can fix this equation here. And the third line here, you have a transversality condition, because like I said, this field, it's a minimum of the gauge orbit, and you have the minimum of this is like the derivative. It's like a tangent of that, and you have a transversality, and you are just implementing in a action this transversality using these gauge fields. And then finally, you have BRC symmetries, because the pure Young mu is a BRC symmetry, BRC invariant, and the OR field, like I showed in the above slide, it's BRC invariant as well, and you can prove that it's BRC. The all action is BRC invariant. Another property from the BRC operator that it's nilpotent. That its nilpotence is very important, because you can define your physical space with that, and of course you can use that you show in the next slide. You can use that to renormalize to show the renormalize or stability of your theory. So the first step when you start your algebraic renormalization procedure is to analyze the symmetries of your action. You have to write all the symmetries of your action. And using the quantum action principle, you have to know that all actions that you have in your classical action, you need to have in your quantum action. So if you don't respect that, you have anomalies, and you can ruin your renormalizability of your theory. But of course, you can renormalize, but you have a lot of problems if you have these anomalies. You have to create another tricks to solve this problem. But here we're just showing in basic way what's the procedure. After that, you can write down your Slavnov-Taylor operator, and this, of course, this is Slavnov-Taylor operator is just the integral form of the BRC symmetry, and you can write that in an integral form just to use in equation 9, because it's more easy to calculate things. And you have the same nilpotency that BRC is just the BRC, the same property that BRC operator S have, the Slavnov-Taylor have too. So when you have your Slavnov-Taylor, you can write down your counterterm, and you have two parts. You divide your counterterm in two parts. You have the cohomology part, and you have your non-cohomology part or trivial part. Some researchers tell that like a trivial or non-trivial part, just because you use the nilpotency here, and so it's trivially zero if you apply. So just because that. But the interesting thing, the physical thing behind that is just because the cohomology part is all particles that you observe, for example, in the real world. And this part, you have the ghost particles, just particles that you use to calculate things, but does not exist in the real world. So, and of course, you use these ghost numbers for that. It's important to calculate things, and your counterterm need to respect the symmetry too, the ghost number, and have to respect another symmetry. It's a symmetry, the rotational symmetry of the supercharge, and it have to be zero in your counterterm. So when you have all the words identities, it's okay. And you have your Slavnov-Taylor, you start writing your counterterm. You can write that in a operator form or a matricial equation that have just this matrix, operator and another matrix here. And you can write your counterterm like that. And the equation 11 is just the usual renormalization procedure. You have a bare action, and your bare action is just your action plus your counterterm that you use to eliminate all the divergence that have in your action. So using 10, inside 11, you have your action plus that. You substitute just a counterterm with that, and you can factor out that 1 plus epsilon r, and you can show using the properties of function that the renormalization of the action is the same of renormalization of the fields. So it's very easy to do that using this operator, because you don't need to calculate all the terms of your action to see some term, individual term that you say, oh, what's the renormalization just of the super gauge field? Just to use that in your field, it's a shorthand notation for that. All the fields that I present in the above slide, and it's done. It's done. You have your renormalization, you have your stability, all the terms that you can cancel your infinities, and now we are coming for my conclusion in future work, and we can show that we construct a supersymmetric non-abelian BRC invariant composite field. This is very good because you can use that to construct a BRC invariant massive model. It's very useful to study some stuffs in low energy Yang-Mills theory. And we showed that this model is renormalizable to all orders of perturbation theory. And it opens, like I said, it opens a big possibilities to investigate some things like a phenomenon of Gribov in a low energy Yang-Mills series. You can extend that Gribov-Zwanzig setup to n equal 1. And you can, of course, use some models from Seiberg-Witten with confining using monodromies. They calculate this in another way, and you can use the tools of quantum field theory to calculate, and you can compare that, and can work in n equal 2 is a confining supersymmetric theory, have a lot of interesting features there to analyze and to calculate, and n equal 4 too is a finite theory. So it opens a lot of possibilities, and that's it. I would like to thank the FAPESP for the support, and I will show some reference that I used to do my presentation. You have the numerical analysis in lattice QCD, the frontier examined in Professor Gutierrez, and our work that we published for that I used for this presentation, and I have the main book that I used is a very good book. If you are interested about algebraic normalization, it's very clear book if you want to understand the renormalizability of the theories, the Professor Piggy and Sorella. And have the Bible of the supersymmetry, the book made by Professors Gates, Grisar, and Rochek. And yeah, that's it. And I would like to thank everybody for listening and coming for my presentation.
Okay, thank you, Ozório. We have time for questions. Let's check in YouTube. No questions. Questions. Okay, João.
Hey, Ozório.
Hey,
thank
João.
you so much for being here. Thank you so much for the nice presentation.
Thank you. Thank you.
I would like to ask a quick question. If you could use this kind of procedure for renormalization that you show, in theories also with high spin terms, or those theories that try to map graviton or try to describe gravity, quantum gravity, let's say. If you could use this kind of tools there too.
Yeah, it's a general framework that you could use in all quantum theories. In the Sorella books, they in the end of the book they calculate things in string theories and they loop quantum gravity. It's a general. It's just a quantum field theory. You can use if you have symmetries, if you have word identities, there's a Lyapunov Taylor. You can build your quantum term and calculate things.
Nice, nice, very nice. Thank you.
Thank you for the question.
Okay, thanks Ozório for this very nice talk.
Thank
very
you.
Interesting topic.
Thank you.
And I think now we finished, right, Ron, this section, and we are back at 4 p.m. Brazil time, right?
Okay.
Yes, and now we have a break. So I'd like to thank the alumni from UFCG who presented in this section. Was really a pleasure to see all of you and see that you are doing quite well in your research career. And I wish the best for all you. And we are really proud not only to have you here with us, but for the things that you are doing and showing our name outside of Campina Grande. So this is really important for us. So thank you so much and wish the best for you all, guys. It was really a pleasure.
Yeah. Okay. Thank you also. Bye.
Okay, so now I'm going to, well, I guess we can still live at YouTube, but if everybody wants to drink some water, have a break, then we go back at 4 p.m. Okay, with the next talk, and after that we're going to have the video posters section. It's not going to be a presentation as we told before, just discussions with the video poster authors. So please feel free to enjoy us there at the video posters rooms. So that's it. I'm going just to stop the recording here, but I'm going to keep live there at YouTube.
João, o próximo é o Wagner. O próximo é o Wagner, né? Wagner Oliveira.
Isso, Wagner chegou?
Ele chegou, não. Pelo menos aqui na sala. Eu não sei se ele está em outro lugar.
Are you there, Wagner, among the participants? If you are, please raise your hand. Wagner, se você estiver entre os participantes e quiser levantar sua mão.
Bom, ainda falta meia hora, ele deve aparecer.
Okay. De qualquer modo, eu vou escrever aqui para ele novamente.
Vou dar assim aqui, bebê.
Oi, João.
Well, hello everybody. So welcome back after our break. I'm just going to start the recording here. Guess that. Yes, Wagner is here already. Okay, so in 3 minutes we can start the last section of this afternoon.
João, should we test Wagner Oliveira's slides? Just make a test.
Hello.
Hey, Wagner.
Hey, João. How are you?
Fine. Is everything okay there?
Yeah. Trying to survive in this pandemic. Yeah.
Good. Thank you for coming. It's a pleasure to have you here with us again, even this situation. So it's the good side of this situation.
Yeah. So can you hear me and see me normally?
Yes, we are hearing very okay and seeing too. If you would like to just to test the sharings.
Yeah.
Share your screen.
Just give me a minute so I can.
This is the green button here in the this toolbar here.
Okay, share the screen. Okay.
Perfect. Nice. Oh, very nice. Okay, so I'm going to start the recording. So welcome back again here in the last section of the ICP 2020. So we have the pleasure to receive another former student from UFCG. Now he's doing his PhD, and I will let Professor Carlos Bessa to introduce our next speaker, Wagner Oliveira. So Professor Carlos, the word is yours.
Hey, Wagner, welcome, and thanks a lot for your to give us this talk. Let's give just a brief introduction for Wagner Oliveira. He's studying his PhD at Universidade Federal da Paraíba, in João Pessoa, and at Istituto Nazionale di Fisica Nucleare in Italy. And his research interests are fermions, antidecided spacetimes, and cosmic strings. And he was a master student at this university, Universidade Federal de Campina Grande, and he was supervised by Professor Eduardo Passos. Okay, Wagner, you have about 25 minutes, half an hour to show us your subject, okay?
Okay, thank you.
Okay, thanks.
Thank you, all the organizers for the invitation. Today my talk has the title "Induced Fermionic Currents in Untitled book with a cosmic string and a compact dimension." This talk is based on the recent paper published in European Physics Journal, C. And it's a collaboration between Professor Stefano Bellucci from Istituto Nazionale di Fisica Nucleare in Italy, myself, and Professor Eugenio Ramos Bezerra di Melo from Federal University of Paraíba. So the outline of my talk is, in the first part, I give some introduction with some motivations and present the problem set up. In the second part, I I present the induced vacuum currents, and in the third and last part, I give my conclusions. So, okay. So our goal is to investigate the combined effects of non-trivial topologies and gravity on local properties of quantum vacuum, such as current test. This quantities appears because the vacuum, the fields in the vacuum, the quantum fields in the vacuum are perturbated by stuffs such as non-trivial topologies and gravity. So the theoretical framework that we consider to study this subject is that we consider matter that matter fields are quantized, that the curved background is classical, so we consider general relativity. It's also possible to investigate the back reaction on the curved background by plugging back the corrected energy momentum tensor. And this hybrid framework, it's an important step towards a theory of quantum gravity. Okay, so why anti-de Sitter? Anti-de Sitter is a solution of ISP field equations in the presence of a negative cosmological constant. So this is a quick definition. Some motivations for consider this background, it's that's a maximally symmetric spacetime, which allows us to solve a lot of problems in exact form in quantum field theory. Besides, it plays a fundamental role in anti-de Sitter conformal field theory, which relates string theories or supergravity in the book of anti-de Sitter with conformal field theories living on its boundary, on the boundary of anti-de Sitter. Okay, another ingredient that we consider is cosmic strings. A quick definition of these objects is that they are linear topological defects arising within the context of Grande unified theories, and they possibly could have been produced in the early universe as a result of symmetry breaking phase transitions. So a common characteristic of Grande unified theories is the formation of cosmic strings during symmetry breaking. Okay. Some facts about cosmic string. Observational data coming from the cosmic cosmic microwave background radiation has ruled out cosmic strings as primary source for primordial density perturbation. So it made a lot of people lose interest on this topological defect. But recently, a proposal of a variant mechanism for formation of these topological defects in the framework of Brane inflation has renewed the interest on cosmic string. Besides, cosmic strings are candidates for generation of physical effects, such as gravitational lensing, generation of gravitational waves, and high energy cosmic rays, and etc. So it has large implications in high energy physics. Momentum tensor, where the mu0 is the linear density of mass energy of the cosmic strings. This parameter is connected with the energy scale in which the symmetric breaking occurred and the formation of the topological defect took place. Okay, in cylindrical coordinates, these topological defects are represented by this line element. So if you redefine the angular variable, you now have a angular variable that ranges between 0 and this and this value. Okay, so this is call it a deficit angle. So cosmic strings produce this deficit angle. Okay, but well, for an observer near the string, he's not able to say to feel the cosmic string by gravitational way. But if this observer or a particle comes from a distant point close to the string, you perceive, you see this conical structure of the space-time. So it has implications like two images, double images from objects behind the string from the perspective of an observer. Okay, so next I would like to talk about extra dimensions and compactification. So a characteristic of many fundamental models trying to unify of models, which has this feature, which brings compactification, extra dimensions, are Kaluza-Klein type models, which the extra dimensions are accessible for all fields, and brane world models, which part of the fields are localized on the brane, and gravity is free to move in the brane and in the book. Okay, so the simplest model to consider compactifications in quantum field theory is by imposing identification conditions on the fields. So two common identification conditions are periodic boundary conditions, in which the field must obey this relation, and the second one is anti-periodic boundary condition, which the field obeys this relation. So basically, what is happening here is that first we compact an Euclidean dimension, okay, which the field lives, and to a circle, okay, and we impose that the fields obeys this relation. So the field now has this configuration, this topological configuration. And in the case of the antiperiodic boundary condition, it has this shape, okay? The field in these two topologies, a trivial one and non-trivial one, they are inequivalent. And it gives interesting effects in quantum field theory. It changes the spectrum of vacuum fluctuations. Okay. So the problem set up. So we have considered in the paper an anti-de Sitter space-time in 1+4 with a cosmic string. It is described by this line element. Okay, and the parameter Q here codifies the presence of the cosmic string, and it's related with the linear density of mass by this relation. The cosmic string is placed along the y direction, okay, Again, it's an infinite straight line of 0 beta. It's interesting to write this line element in Poincaré coordinates by using this coordinate transformation. And by doing this, we get a line element which relates the anti-de Sitter spacetime with the Minkowski spacetime by a conformal relation. So this overall factor here is a conformal factor. This is interesting to verify our results. And here I would like to just underline two values of double V that have name. The first one is double V equals 0 until the Sitter boundary, and double V goes to infinity until the Sitter horizon. So we are interested to study fermionic vacuum currents. So we have to consider the Dirac equation curved spacetime. And in this sense, we consider this equation, okay, which is coupled with with the magnetic field, and also this parameter as tilde appears, and it assumes two values, and these two values correspond to the two irreducible representations of the Dirac matrix in odd spacetimes. In the paper we have choose S tilde equals 1, which simplify the calculations, but the choice has no physical consequence. And here I just give a description of the mathematical objects that we use in this equation. We have to introduce a tetrad basis in order to build, to construct the Dirac matrix in curved space-time, and as a consequence, ultimately the spin connection. Okay, so besides that, we also consider quasi-periodicity condition. Okay, so with the extra dimension that we have considered, we compactified it on a circle by identifying the 2 points, 0 and L. And besides that, we impose that the field we have the untwisted field or periodic boundary condition. And for beta equals half, we have the twisted or field or the antiperiodic boundary condition. Besides that, we consider magnetic fluxes in our system, and they are put by considering in the system, they are put they are considered by two vector fields, one A phi, which correspond to a magnetic flux along the string, and AZ that is a magnetic flux running the center of the compactified dimension. So in this figure, we have an illustration of what is happening in the compactified axis. So you can see that the magnetic flux is localized in the center of the circle. Okay, so with all these elements, we are in the position to solve the Dirac equation, and the positive and negative energy modes are given by this fermionic field. Okay, sigma is the set of quantum numbers, and the energy is given by this equation. For a normalization condition, we have this factor, and I would like to underline the discretization of the momentum along the extra dimension, which is now quantized due to the quasi-periodicity condition. Okay, and now this momentum depends not only on the having the fermionic modes, we are in position to calculate the fermionic currents. Okay, so we sum, in order to calculate this vacuum expectation value of the current density, we sum over all quantum numbers of the field. Okay, so for the components, for the charge density and the current densities along the radial direction and double V direction or Poincare coordinate, the results are trivially vanishing. Well, so the first non-zero current density is the angular, the azimuthal current density, and we can split this wave into two components. A first component is induced purely by the cosmic string without the compactification. The second one is induced by compactification. So let's discuss each one separately. The first one, induced by the cosmic string, is given here. Okay, here are some definitions, and well, some notes on this wave. First of all, this term here is just non-zero for Q greater or equal than 2. This current density only exists for alpha 0 different from 0, and this is a Hanorov-Bohm effect, Hanorov-Bohm-like effect. Okay, and where this alpha 0 came? It came from the decomposition of the parameter alpha, okay, given in the order of the fermionic modes. And it decomposed into two numbers. This n0 is an integer number, and alpha 0 is a fractional number. We can redefine and include this n0 in the summation over J. Cosmic string. So in this image, I have plotted we have plotted this wave, and we see the periodic behavior of the current density produced by the cosmic string. Besides, we also see that the intensity of this current density increases with the parameter Q associated with the current density. And it's a 0 for alpha 0. Okay, so asymptotic and numerical analysis. So for points close to the string, we have we have a divergence, which is to the fifth power of the inverse of the proper distance unities of A. And for points far away from the string, we have this relation. In the graphic, we can see this illustrated. As you get close to the cosmic string, this wave diverges. As you go away from the string, this wave vanishes. Okay, so now, sorry, the current density induced by compactification. We are still treating the azimuthal current density. So it's given by this relation, but now we have the presence of the parameter associated with the compactified axis. Okay, and I would like to remember here just that this parameter depends on the quasi-periodicity condition and on the magnetic flux along running in the center of the circle enclosed by the compactified axis. A feature of this current density is that it is finite for r equals 0, differently from the first term, which is divergent. Okay, so here we have plotted, and we can see here the periodic behavior. It's an it's an even function for beta tilde, and it's an odd function for alpha 0. And this is expected, since if we invert the magnetic flux along the string, we expect that the current density change its direction. An asymptotic behavior for this component is that it decays for large values of the extra dimension. And it's expected because as we take large values of L, the topology lose its properties. I mean, you go from a circle to a normal topology, a trivial topology. Okay, now we have the axial current density. This current density is induced by compactification. Okay, and it appears because the compactified axis along with the magnetic flux change the spectrum of the vacuum fluctuations. So in the limit L goes to infinity, it vanishes, which is expected. Similar to the azimuthal current density, we can also split this VEV. The first term is this one, is purely induced by compactification because we don't have the presence of the parameter associated with cosmic string and with the alpha 0. The second term has also, it's induced by the compactification, but also has influence of the cosmic string and the alpha 0. Okay, so some notes on this VEV is that it's 0 for in the absence of magnetic flux, and for beta equals 0 and beta equals half, which correspond with respectively to one twisted field and twisted field. Okay. And for beta equals 0, this VEV is a periodic function only of the magnetic flux enclosed by the compactified axis. And here we also have illustrated this behavior. So we can see here that this VEV is an odd function of the beta tilde, and it is an even function of the alpha 0. Okay, so my conclusions. We have calculated the VEV of the current density along the azimuthal direction. Okay, this VEV can be decomposed in two components, cosmic string and compactified. Both are odd functions of alpha 0. Well, it is a Haronov-Bohm effect type. Okay, so this is about the term induced by the cosmic string. The term induced by the compactification is an even function of beta tilde, as expected. We also have calculated the VEV of the axial current density, which has topological origin. And it's also expressed as a sum of a pure topological term and another term which is not only induced by the non-trivial topology of the compactified axis, but also has influence of the cosmic string and the magnetic flux along the cosmic string. Both contributions of the axial current density vanishes in the limit of large extra dimension, which is trivial topology. And well, the non-trivial topology induced by the cosmic string increases the intensity of the vacuum cavities. So the conical structure of the induced by the cosmic string in the space-time modify the spectrum of vacuum fluctuations. We change the VEVs of the physical observables in the vacuum. Okay, that's it. Thank you.
Okay. Thanks, Wagner. Thanks a lot for this.
Thank you.
Very nice presentation. So I think we have time for questions. Questions here. You can write in the Q&A section. To participants, let's see in YouTube. Any questions? So these topological conditions it could be possible to try in more than one dimensions, for instance. Like,
yes, why not? Yes, it's possible in 1+1, but yeah, I don't understand how, which system you would like to study.
yeah, because this is
usually people.
Field, right?
It's a scalar field. Yes, yeah, it's possible to study these quasi-periodicity conditions. But usually people use it to study it in 1+2 dimensions and study the applications in condensate matter like graphene physics.
Yeah, that's what I was thinking. Okay, question.
Yes, Wagner, I have one question. Yeah. So thank you before the question. Thank you so much for the nice presentation, and also for the nice work you have been doing, and for the success that we have been acquiring your career too. So this is really awesome to see. And then I would like to ask, well, first, when you talk about this cosmic string with a magnetic field, I mean, it's a little bit hard for me to see this physical scenario. So could you explain a little bit with more details? How could it, let's say, imagine a physical scenario with this cosmic string and let's say a source for this magnetic field, for instance?
Okay. So first of all, cosmic strings induced a non-trivial topology in the space-time, which is this conical topology. This by itself, it's already enough to change the spectrum of quantum fluctuations in quantum field theory. Besides, we consider this magnetic flux running along the string's core. And this magnetic flux, we put it by hand, but this magnetic flux actually is a theoretical prediction by Witten. Now I don't remember the year, but this cosmic strings naturally carries this magnetic flux. So I don't know if I answered your question.
Okay. It's fine. I also would like to know, for instance, in the graphic that you show about the current oscillating, I saw that it depends on the parameter beta. So, for instance, could you create another, let's say, oscillatory behavior for the current by changing beta?
Yes.
Or even cancel the oscillatory effect in some extreme limit?
So yeah, returning to the quasi-periodicity condition, this beta, different values of it correspond to different topologies that the field must obey, that the field lives. Like as I put here, for beta equals 0, we have this circle topology, and for beta equals half, with this kind of strange topology, but it's a Mobius strip type of topology. So yeah, you can have different shapes for this extra dimension, and it modifies the spectrum of vacuum fluctuations along this dimension. The other question, sorry, can you repeat?
What I was saying is, if you could even cancel the oscillatory effect in extreme condition for beta.
For beta, not assuming beta. Okay, if we consider large values of the L, of course, these boundary conditions has no validity anymore, because we are not compact. We are not considering a compact dimension. Okay, but for what I understand, it has no way to cancellate the oscillations, because for all values of beta inside this.
Oh, I see now. I guess it's, well, the internet is failing a little bit, but I realize that beta needs to be between 0 and 1, so this is supposed to have oscillatory effect always. It's not possible to oscillate beta fast enough, maybe, to cancel oscillatory.
Sorry, João, the connection here is a bit unstable, and I didn't hear. I didn't hear your question. Can you repeat, please?
Yeah, sorry. What I was saying is that maybe I realized that now that beta is constrained to be between 0 and 1. So this means that you're always going to have a finite oscillatory effect.
Yes. For all values of beta, yes.
Oh, thank you again, Wagner. I guess we have one person here with, who raised his hand. So Lucas, if you want to make a question, I'm going to allow you to speak.
It's, what is the question? Sorry.
Yes, I allowed one participant to speak, so he can make the question with the microphone.
Okay.
Lucas, você tá aí? Quer fazer uma pergunta pelo microfone? Pode fazer em português mesmo. Acho que ele desistiu. Ok. Bom, de qualquer maneira, muito obrigado, Wagner, pela palestra. Foi realmente muito boa. Parabéns pelo seu trabalho.
Obrigado aí.
Eu acho que a internet do Wagner caiu novamente. Eu acho que você voltou agora. Mas obrigado novamente, Wagner. Caiu novamente. Obrigado.
Obrigado, João. Obrigado pela oportunidade.
Okay, thanks a lot, Wagner, for this very nice talk, very nice subject. Congratulations.
Thank you.
Now, let's introduce the next speaker in the last from this section. Is Clarissa Siqueira. Hi, Clarissa. Let's introduce her. She had her PhD in physics at Universidade Federal da Paraíba and Max Planck Institute in Germany. And she was postdoc at International Institute of Physics in Natal, Brazil, and currently she's a postdoc at Universidade de São Paulo in São Carlos, Brazil. And her research topics interests are dark matter detection, gamma ray, and particle physics. Okay, Clarissa, you have about 30 minutes.
Yes. Thanks, Carlos, for the nice introduction. Let me try to share my screen here.
Yeah.
Can you see?
Yes, we can see, and we hear you very well.
Let me try again. Now it's okay?
Yes, very good.
So, first of all, I would like to thank the organizers, especially João, for the invitation. It's a pleasure to present my research area here for you. And I will talk today about the particle dark matter and how can we detect it. But I would like to start asking why particle dark matter. So we have several evidences for the existence of dark matter, actually. They come from galaxy rotation curves, from the bullet cluster, which is the collision between two clusters. They come from structure formation and from the CMB and also the BBN. And all of them points toward some characteristics that some kind of particles need to have to be the dark matter, the good dark matter candidate. So they need to be neutral, they need to be weakly interacting, they need to be non-baryonic, cold or warm. They need to compose 27% of the energy budget of the universe, and they also need to be stable. So the point is, if we have a particle which fulfill all these characteristics that are present here, they will be a good dark matter candidate, and they can explain all of these evidence that we can see here. So we actually have this kind of particle. The main candidates is the weakly interacting massive particles. They are called WIMPs. And this, if we have a WIMP particle, we can fulfill all of these requirements. So, but how this particle dark matter can be produced? How we can get this abundance of that dark matter that we observe today? So basically, we assume that we have the evolution of the number density of the dark matter particle is driven by a Boltzmann equation, and the standard mechanism that we use for WIMPs is the freeze-out mechanism. So we assume that we have the M particles in thermal equilibrium with the standard model particles in the beginning of the universe, and this is represented in this plot by this constant line here. However, when the universe is expanding and cooling, the standard model particles has no energy to produce dark matter particles, and we have this decrease here in the abundance of dark matter in the universe. So at some time, the expansion rate of the universe is faster than this interaction rate, and we have this decoupling of the dark matter, and the abundance of the dark matter remains constant until today. So associated to that, we have this cross section. And from the CMB, we have the correct abundance that the dark matter needs to have, which is given by this number here. So what we call the WIMP miracle is when exactly because the cross section associated with the correct abundance of dark matter in the universe can be tested by the current experiments. So this like complete why we study, why we look for dark matter particles today. if we have a dark matter particle, how can we detect it? So we have basically three ways to do this. This is driven by these arrows here. One of them in this direction, we have two dark matter particles annihilating, and these particles produce standard model particles. And we can observe the products of this annihilation here in our detectors. The other way can be the what we call direct detection. In the direct detection, we have we know that we are embedded in a dark matter halo. So we can expect that this dark matter particle can scatter with our nucleus in our underground detectors. And the other way is in this other direction. So we can have, for example, in colliders, we have the collision between standard model particles like the proton and the LHC, and these particles collide, producing these dark matter particles. And I will talk a little bit about it now. So this is a picture of the LHC. The LHC, it's the biggest experiment nowadays. We have here, it has a circumference of 27 kilometers. And here are the detectors, the ALICE, the ATLAS, the LHCb, and the CMS. So they are looking for dark matter particles in these colliders, when we have basically two proton collisions here, and we have this bunch of particles here in the detector. So as I told you before, the dark matter has a characteristic to be very weakly interacting. So the detector cannot, the dark matter cannot leave a trace in the detectors. So the way that we can assess the dark matter in this kind of collider experiments is, for example, when we have a particle here leaving the detector, leaving a trace in the detector, and for example, on the other side we have nothing. So we can via energy conservation, we can suppose that there is another particle here in the other side, and this particle can be a dark matter candidate. So before I start to talk about the other two ways to look for dark matter, I will talk a little bit about the dark matter distribution in our galaxy, for example. Because for direct detection methods, we need information about, for example, the density distribution of the dark matter in the medium, and also the velocity of the dark matter. So the Milky Way is a very complex system, which is composed by gas and dust, which we call intergalactic medium, and also stars and the dark matter. So here we have a picture of our galaxy. This is the central region of the galaxy. We are located exactly here at this point, approximately 8.5 kiloparsec from the galaxy center. And here we have, for example, the dwarf spheroidal galaxies, which are good targets for the search for dark matter particles. And we have a huge dark halo represented by this black spherical region around surrounding our galaxy. So, for example, for direct detection, we need information about the distribution of the dark matter in the location of the Earth or of our sun. In the case for direct detection here, we look usually at the galaxy center, which are a very dense dark matter region, and also dwarf spheroidal galaxies. So the distribution of dark matter in our galaxy is not trivial to get. We have they call it N-bar simulations in order to get this, and we have several profiles that some independent groups do this kind of analysis. And the most common are the NFW, the INASTO, the Burkett, and the isothermal that are represented here. And here we can see that from this region, this is the central region of the galaxy. It is the density of dark matter. So in the inner region of our galaxies, we have a huge discrepancy between the several dark matter density profiles in our galaxy. And for the external region, we can estimate via galaxy rotation curve. So all of them converge for the same about the same value. So here from galaxy rotation curves and from simulation, we also can get some information about the density of dark matter in the region of the sun, and also the velocity distribution of dark matter here. So we have some targets, as I already told you. The first one, the galaxy center, which is predominantly composed by dark matter. We also have the dwarf spheroidal galaxies. They are really important because they has a high mass luminosity ratio. So they are predominantly composed by DM. So if we look at some dwarf galaxies and we observe some products of annihilation of dark matter, in this case, we can say for sure that it's a signal of dark matter. They are galaxies that orbit the Milky Way, and they are located between 15 to 250 kiloparsecs from the galaxy center. They are located here. And so we have also not just targets in our local galaxy, but also outside. For example, we can look for signals of dark matter from the Andromeda galaxies. They are usually looking for the, signals from dark matter from them. Also from the Virgo cluster and the Coma cluster that are located in the Virgo supercluster. So it's a little bit harder to look for dark matter in these cases because they are not close to us, and we can have a lot of background related, and it's hard to distinguish between a signal of dark matter and the background. With these ingredients at hand, we can talk now about the direct detection of WIMPs. So as I told you, we are embedded in a huge dark matter halo in our galaxy, and we can expect that these kind of WIMP particles can interact with our nucleus in our detectors, underground detectors. And this will provoke like ionization, excitation, or heating, and they leave an observable signal at our experiments with an recoil energy close to 30 keV. So here a little bit of the theory from the interaction rate. We have a part that depends on the experiment. We have also the part that depends on the astrophysics and the distribution of dark matter in the galaxy, as I showed before. Sorry, not in the galaxy, but in the location of the sun, and also the velocity of dark matter. So it also depends on the interaction model. So we need to have a model behind, a theoretical model to produce that have this kind of WIMP particle. Something interesting is that this cross-section depends on the mass number. So this is why usually experiments looking for WIMPs generally use heavy nuclei like xenon for example, for the Lux experiment and the xenon 1 ton. And using some standard values, we can see how what's the value, what the estimated event rate that we can get, which is given by this number here. And for example, this is per year. So this is why we have a huge quantity of the nucleus for this kind of dark matter detector. For example, the last upgrade of the xenon is to 1 ton of xenon in order to increase the sensitivity of the experiments to a dark matter interaction. So, and why, how this kind of experiment can be constructed. So usually they have a lot of layers, like we can see here, a huge structure, and they are underground detectors in order to avoid some background, because especially for the neutron in this case, because neutron can mimic a dark matter signal. So they can block this, they need to block this kind of background. And basically this is how this detection happens. Téssio talked a little bit about it on his talk. Basically, a particle of dark matter can come and entering the liquid xenon phase, and they interact with the nucleus, and with this interaction we will emit like scintillation light, and also we have some ionized electrons, and these electrons will be drifted until the gas phase of the xenon, and we will interact again, and we have this combination of these two signals in order to say what's exactly the energy, in order to distinguish, for example, from the background, and in order to say what is the exact location of the interaction of the dark matter particle. So until now, we do not observe any signals from WIMPs on the xenon or Lux or any other experiments looking for direct detection of WIMPs. So this is a plot which excludes the some part of the parameter space of the dark matter particle, in this case WIMPs, and versus the dark matter mass. So if we have a particle dark matter, for example, in our prediction of our model from with approximately 100 GeV, and if it has a cross section of 10 to minus 44, it will be excluded by these experiments. So these are the most stringent limits that we have on WIMP particles. All above this region here is excluded in a good part of the standard models with WIMPs has been probed by these experiments. So here in the dashed lines, we have the prospects for the future experiments. And also here we have the called neutrino flow, which is basically a limitation from the experiment, that in this region here, this orange region here, they cannot distinguish between a signal, an interaction from neutrinos or dark matter. So they cannot distinguish. Of course, there are some theoretical efforts or in experimental efforts using directional detection in order to avoid this region here. But this is a quite stringent scenario for the standard with dark matter. So with this, we can proceed to the indirect detection searches. Basically what happens when we have dense regions of the sky, we can have the annihilation of dark matter particles, and this annihilation will produce we expect this production of this kind of standard model particles, and they will hadronize and decay. And what we can see in our detectors is the stable products of this annihilation, which are the gamma rays, for example, the neutrinos and the antimatter. So the advantage, for example, of having neutrinos and gamma rays is that they are neutral, and they usually trace back the source. So they give information about the location of the source because they are not deviated by strong magnetic fields in the galaxy. And we have also this information. And also the gamma rays are good sources for look for dark matter, because they are easy to detect. Neutrinos are really hard to detect. So usually the stringent limits comes from the gamma rays. So, but why the gamma rays? Because we have all the electromagnetic spectrum here. We span over radio, over microwave, infrared. The visible light is just in this region here, ultraviolet X-ray, and the gamma rays. So usually due to the high mass of the dark matter, usually around the scale of GeV or TeV, the products of dark matter comes in this gamma ray region, and we can observe that basically in two ways, through the satellites which are located here basically, and with the ground detectors. We have also ground telescopes here, but the gamma rays, which are really energetic particles, they usually do not reach the ground. So they interact with the atmosphere, with the medium, and they produce this kind of shower here. So in order to detect the dark matter particles with ground-based telescopes like the HASS and the Future CTA, we need to look for these products of these cascades and reconstruct the primary photon that enter the atmosphere. Going to the theoretical point of view, this is basically the gamma ray flux that we can expect from an annihilation of the dark matter particle. In one side, we have a part which depends on the particle physics model related, and in the other side, we need to have information about the medium, which is encoded in this J factor here, and we need information about the distribution of dark matter in the galaxy. So these basically are the main ingredients that distinguish, for example, the shape of the spectrum. So depending on how which particle the dark matter annihilates into, we have a different shape of the spectrum. So we can know which kind of interaction the dark matter is having with the standard model particles, and also how from where these particles are produced. And also, as I already told you, we have the point as the spatial distribution of the dark matter in the galaxy. So in the inner region of the galaxy, we have this huge discrepancy between several dark matter density profiles, but the most used nowadays is the NFW and NASTO, which has this more cuspy profile in the inner region of the galaxy. So basically are the main points that we can discriminate as dark matter signal from gamma rays. And here in the cross section in the mass of the dark matter, we have information about the dark matter model. So, and about the local targets, I already told you a little bit about the dwarf spheroidal galaxies and also the galaxy center. The advantage of dwarf, each one has its advantages. For example, with dwarf spheroidal galaxies, we know that they are predominantly composed by DM, and they have this advantage to be very clean targets for dark matter searches, but because they are free from background. So if we look at the location of a dwarf spheroidal galaxies and we see some signal, some gamma ray from there, it will be probably a signal from dark matter. And the stringent limits comes from the dwarf spheroidal galaxies, especially from the Fermi-Lat experiments, which are running, getting results from the last decade. So the other region is the galaxy center. The galaxy center is a region which has a huge DM density, higher than the dwarf spheroidal galaxies. However, there is a problem with them because it's located into a really bright region of the sky where we have a lot of other emissions from the background, for example. So it's really hard to distinguish between a signal from dark matter and a signal from the background. So today we have these two experiments, Fermi-Lat and HAS, that are currently working, and they are putting several limits over the annihilation cross-section of the dark matter particle. And we also have the future CTA that will cover a huge energy region and will give a really better sensitivity compared to the current experiments, as we will see. So these three experiments, they work like in a complementary way. If you see, they cover different energy regions, so they can put limits in different regions of the dark matter parameter space. As we can see here, this is a plot combining several results, including results from the LHC, results from the Fermi-Lat, using dwarf spheroidal galaxies as targets for the search for dark matter. And they are putting stringent limits on this parameter space, since we do not observe any signal from dark matter until now. So here in this this gray region here is the region that provides the standard WIMP cross section that provides the right relic density of dark matter today. And here we have also the limits from the HAS, which are quite stringent, but not too much stringent. All of these limits are constraining all this region above these lines. So the future CTA, this is a prospect for the CTA. It will cover a huge region, and it will have a very higher sensitivity to dark matter particles compared to the current experiments. And it will be able to probe this region that provides the right relic density. So there's a lot of expectation over the CTA experiment because they can probe actually the existence of dark matter. So, but until now, I talked a lot about the possible ways to detect dark matter, but until now, I told you that we do not observe any signal of dark matter, and we are just putting some limits on the dark matter parameter space, the cross-section and the mass of the dark matter. However, some of these indirect experiments already observe some excess that until now cannot be explained by the background. So they can be a signal, from dark matter. For example, they has observed at high energy this bump here that can be explained with dark matter models with WIMPs. And also in the same, all of them were looking for at the galaxy center region. And also there is an excess observed by the Fermi-Lage experiments at lower energy, also at the galaxy center. And here we can see that including all of the background and if we exclude all the background, this small region here survives, and this can be a signal from dark matter. And this has been explored over the years by several researchers. So the other one is the positron axis. Basically, we have this region here, this gray region here, which is compatible with background. However, they are observing this huge bump here, and they cannot explain that using just the background. So they need something more, and it can be also explained by dark matter. Of course, there is another possibilities. As I told you before, the galaxy center region is a really complicated region because we have a lot of background. So it's really hard to distinguish between a possible new signal of dark matter or pulsars, for example, from the background. So I can go to my conclusions. So we have a lot of evidences coming from since the 30s with the Gamma cluster. We have with Vera Hub in the Andromeda galaxy and other galaxies. We have also the Adama result that points towards a possible WIMP candidate, but it's a controversial signal. And we have plenty of experiments trying to look for these dark matter particles around the world today. I can include here, for example, the CTA, the xenons here. And so maybe not until 20 and 24, but in the next decade, maybe we can observe this possible dark matter particle, and this is what we expect. Thank you very much for your attention.
Okay, thanks, Clarissa. Thanks a lot. Very, very nice talk. So let's see if you have questions. I can't see any question here. Let's see in YouTube. Check here. No, nothing in YouTube. So people are too shy this afternoon. No questions for anyone. Thank you, João.
Yes, thank you, Clarissa, again for this nice presentation. It was really fun and really with a lot of nice information about dark matter and clarified a lot of things in my mind also about this subject. So really interesting. And also I'd like to ask about, well, there are several points that I'd like to ask, but I guess I'll just make two questions. One is about this detection that you and Klécio mentioned before in this exon, I guess, experiment.
The xenon one
Yes.
ton.
Yes. Because in this type of detection, what is interesting, well, maybe it's a naive question, but what is interesting is that you have a dark matter particle that is going to interact with electrons there inside of the detector. But
Yes, actually, the WIMP particles interact with the nucleus, not with the electrons. But
okay.
Depending on the mass, if the dark matter is light, is very light, they can also interact with the electrons in the detector.
Okay, so yes, so that is the point, because, well, when I imagine dark matter is a kind of matter that only interacts with gravity, but when you imagine particles, then particles they have a small mass, so small gravity. So how exactly? Well, I don't know if you know these details, but how exactly you can observe a clear signal from dark matter when you imagine these forces in this scale are so low?
This is the point. We are not considering here that the dark matter is interacting through gravity, but through another kind of interaction that can be very weak. For example, one of the first candidates was the neutrino from the standard model. But the neutrino is two light particles, and they interact through the weak interaction. So they could be a good dark matter candidate, but it is too light, and it gives overabundance of dark matter, and it leads to problems also with the structure formation. But the point is, we are not considering that the dark matter is interacting just through the gravity, but because this interaction is negligible. We can see just in large scales, but with another kind of interaction, like the weak interaction, for example.
Okay, thank you. And also, those graphics about the cross section and that you showed, I saw that the cross section area is very small, even in these ones that they are up to 10 to minus 27 and minus 23. So the graphics, they seem to consider small cross sections, but what is impressive is that the mass gap seems to be really huge, because it goes from 10 to 0, I guess, and 10 up to 3 or 4. So is this a feature that, well, is this behavior behind this fact that it's so hard to know exactly what dark matter is?
Yes, this is the point. Actually, if you here we are looking at the candidates which are WIMPs, and the WIMPs goes from the a few GeV to a few TeV, but we have candidates with a sub-GeV mass, or we also have candidates with hundreds of TeV mass. So it's a really large range for the dark matter mass in cross section. So I think we are now looking for WIMPs, because WIMPs has these characteristics that can be detectable. They produce the right relic density, for example, via the freeze-out mechanism. However, we have several other candidates. And for example, if we do not look some dark matter, some WIMP candidates, we have other several candidates. Even the primordial black holes can be also candidates to dark matter. it's improbable that compounds all the density of dark matter today, but maybe a part of that. So we have several possibilities here. We still have several possibilities, but the experiments are closing this region. This is the idea.
Okay. Thank you again, Clarissa. It was a pleasure to have you here with us. And
thanks, John.
Congratulations.
It was a pleasure to present this work here.
Okay, congratulations also for your new position now, and I wish you all the success there in São Paulo.
Thank you very much.
Just Marcelo told you just congratulations and nice presentation. It's not a question, but he wrote here.
All right, thank you.
Okay. So, okay, I think we have another question. Let's YouTube, no. Yeah. So I think it's okay. Great. Thank you, Clarissa. Thanks a lot for your very nice presentation. Clarify a lot of things about this very hot topic.
Thank you very much.
Lot.
Thanks.
Okay. So with this, we finish the sections of the ISP 2020. Now we are going to move to the video posters presentations. So I guess you all are receiving emails about how to access the video poster presentations. And then you can go there and check with the authors about some doubts or any clarifications or curiosities that you have about their work. But before I finish this section, I just would like to say thank you again for the UFCG administration, for all the professors, all the postdocs and researchers that we received here among these days. It was an amazing event, this one, I guess, with a very significant public also. So I would like to thank for all the students, professors, people from several different places in the world who watched these transmissions here with us. And it's really a nice and historic moment for our department to make an event like this. I hope that we can do this event again in near future, and we are going to work on it to try to give to several people around the world again the possibility to be part of our community here in Brazil and bring people from foreign countries also to share the knowledge that they have with us. So it's really a pleasure. Okay, so thank you very much for everyone, and I hope that you enjoyed a lot, especially the students, the opportunity to be part of an international event. We make everything we could to bring you an international event or the spirit of international events in this part of your career. So thank you again, and I hope you join us at the video poster sections.